In this last module, we're going to take a look at the phase diagram and different regions along that phase diagram. A phase diagram basically represents under what conditions, pressure and temperature, would you expect to find all three phases of a substance. What would you expect to find the solid, the liquid, and the gas, and the equilibrium between all of those phases. So for example, under what pressure and temperature conditions would you expect to find the boiling point or the melting point of a sample? So looking at the phase diagram, there are a few different regions that I want to focus in on. And the first that I want to point out is the triple point. The triple point is right here. And as it looks, the triple point is the point where all three phases could be found at equilibrium. Right? The pressure and temperature conditions where all three phases could be found at equilibrium. So I'd expect to find at this exact point right here, at the triple point, I would expect to find the solid, the liquid, and the gas phase at equilibrium. Another interesting point is the critical point here. And you'll notice that that equilibrium between the liquid and the gas, that line stops at the critical point. And so beyond that critical point, we have something unique there. We basically have a supercritical fluid, which is something that demonstrates properties of both a liquid and a gas. So we've stopped becoming a gas, we've stopped being a liquid. We are now something that demonstrates properties of both liquids and gases. And so a critical point, basically at temperatures and pressures above this point, at temperature and pressure above this point, the sample demonstrates properties of both gas and liquid. So kind of an interesting region of that phase diagram. And so here's an example of the triple point of t-butanol in this short video. They're going to start by pulling a vacuum, and so we're going to see the equilibrium between the liquid and the gas phase. And then as we know, boiling a sample is endothermic, so that will cool the solution down. Shortly after that point, the sample will begin to freeze and then boil again, and we'll have all three phases occurring at once. So we'll be at the triple point for t-butanol. So as I mentioned at the first slide when we were looking at phase diagrams, those lines between the different phases, between the solid and the liquid and the gas, those lines mean something. Those lines are the equilibrium basically between the solid and the liquid. For taking a look at the blue line, right, anywhere along this line, it would tell me the pressure and the temperature where I'd expect to find the melting point of this sample. That's what that blue line tells me. Where's the equilibrium under those conditions that I expect this sample to undergo melting, or if I'm going the other direction, what would be the freezing point of this sample? Similarly, the red line is between liquid and gas phase, so that is any point along this line will tell me what is the pressure and temperature of the boiling point of this sample. So similarly, we can work our way across to say, okay, I want to know what the boiling point is right here. Well, at this pressure and this temperature, there's my boiling point. So both of those lines will tell us where can we expect to find that equilibrium between those phases. What pressure and temperature would that be? The last line is this green line down here. That is where I'd expect this sample to undergo sublimation. So going directly from the solid phase into the gas phase. But again, under what pressure and temperature would that occur? So taking a look at this phase diagram for water. This is a little bit different than the phase diagram that we looked at on the previous slide. The previous slide, we had a phase diagram that looked like this, where I have my solid, my liquid, and my gas. And we'll notice the slope of that equilibrium between the solid and the liquid phase, right? We had a forward-facing slope, which means if my pressure and my temperature, I would have to increase temperature to take that sample from the solid phase into the liquid phase. That's nothing new for us, right? We know we have to warm something up to melt that sample, to go from a solid to a liquid. However, for water, if we look at water, the slope of that region is actually quite different. That slopes to the left. And so what does that tell you about water? Well, if anyone in here has ever gone ice skating or plays hockey, right, you're taking advantage of this unique phase diagram for water. Water is unique in that it has a phase diagram where this transition between solid and liquid actually slopes to the left. And what that means is if we're at a sample of water at 0 degrees Celsius, so here I am, 0 degrees Celsius, if I increase the pressure and only increase the pressure of that sample of ice, I'm able to melt that sample. So why do ice skates, why do hockey skates have a really small surface area? To maximize the pressure. So you're taking all of your weight and you're putting it on a very small surface area of that skate. So you're applying an incredible amount of pressure to the surface of that ice. So you're not skating on ice, you're actually skating on a small layer of water on top of that ice. A small layer of water that you're melting by applying pressure to that ice. So water is unique in that we can undergo a phase transition by only increasing the pressure. In the previous phase diagram that we looked at, if you were to be a solid and increase the pressure on that solid, you were going to stay a solid. You normally need to increase the temperature to go through a phase change. But water, because of the slope of this to the left, we're able to undergo that phase change simply by increasing the pressure on the sample. Here's the phase diagram for carbon dioxide. As you can see, it's got different morphology than the phase diagram for water. Carbon dioxide, solid carbon dioxide, is typically known as dry ice. So if you've ever worked in the theater industry and made that fog that comes out, that fog, you're using dry ice. And we can see that because it's got an incredibly large region where I could expect dry ice to sublime, to go from the solid phase into the gas phase. And here's my normal pressure, 1 atm pressure. And so you can see if I have that solid at 1 atm pressure, right, even at very, very low temperatures of minus 80 degrees Celsius, I would expect that sample to sublime right away. All right, so let's take a look at a phase diagram for methane and answer a few questions about that phase diagram. So what are the approximate temperature and pressure of the critical point? Where we expect to find the critical point of this sample? So taking a look, right, the temperature might be about minus 100 degrees Celsius, right, all the way down here. And the pressure of that might be around 80 atm. So here is my critical point. All I want to do is work my way down and work my way across to find the temperature and pressure of that point. What are the approximate temperature and pressure of the triple point of this sample? Here's my triple point. Again, work my way down and work my way across. So my temperature and my pressure. Right, for my temperature, I'd expect that to be maybe around negative 180 degrees Celsius, and for my pressure, about 0.1 atm. And the last question At 1 atm pressure and 0 degrees Celsius, what phase are we? So 1 atm pressure, and I'm going to work my way across until I hit 0 degrees Celsius. Right, so at 1 atm pressure, 0 degrees Celsius, this sample would be a gas phase. So the important things from chapter 11, hydrogen bonding interactions, dipole-dipole interactions, London dispersion forces, ion-dipole interactions. Be able to identify what samples would have what intermolecular forces, and then based on the strength of those intermolecular forces, what would the boiling point of the sample be, for example. Also, we looked at phase diagrams, so simply interpreting a phase diagram, being able to determine what would be the temperature and pressure of the melting point or the boiling point, or given a temperature and pressure, what would the phase of that sample be. We looked at the transitions as well, from taking a sample and heating it up from a solid into the liquid, going through a phase change, and then heating a liquid, and then going through the phase change again of a liquid into the gas. So know when to do what calculation for either Q equals MC delta T for heating a sample, or going through a phase transition and the calculation you would use there to determine the energy transfer for that process. So on Wednesday, we're going to start chapter 17. We're going to take a look at thermodynamics.